Do you think the greatest obstacle on the journey to Saturn is the enormous distance or its famous rings? What about the fact that this planet has no solid surface, and that if you attempted to land on it, you could sink into an ocean of scorching gas? Today we are going to embark on a journey to one of the most beautiful and, at the same time, most dangerous planets in the solar system. You will discover why the temperature at Saturn's core reaches nearly 12,000 degrees Celsius and exceeds the temperature of the Sun's surface. We will find out whether any form of life could exist on Saturn, and by the end, you will understand why it is impossible to return home from this planet, even aboard an extremely powerful spacecraft. Ready to explore a world where the laws of physics, as we know them, seem to turn against humanity? Then let's begin our journey. But don't forget to like and subscribe to our channel. First of all, try to imagine the magnitude of this trip. The distance between Earth and Saturn is not constant because both planets continuously move in their orbits around the Sun. When Saturn is closest to Earth, the distance between the two worlds is approximately 1,200,000,000 kilometers. When they are on opposite sides of the Sun, that distance becomes even greater. For comparison, the Moon is about 384,000 kilometers from Earth, yet it already seems incredibly far away. This means Saturn is roughly 3,000 times farther from us than the Moon. This is not just an impressive number, but a real obstacle that directly affects travel time. Even the fastest spacecraft take years to cover this distance. For example, the Cassini probe took about 7 years to reach the vicinity of Saturn. The legendary Voyager 1, which merely flew past the planet during its mission, required approximately 3 years and 2 months to reach that region of the solar system. And we are talking about unmanned spacecraft. Now imagine a human being spending several years confined inside a spacecraft. In addition to the enormous psychological strain, there is also a very serious physiological threat. Extended exposure to a microgravity environment causes muscle atrophy and loss of calcium from the bones. On top of that, space radiation has extremely harmful effects on living tissue. But let us assume that through some technological miracle, all these problems have been solved, and that we have developed a spacecraft capable of transporting a crew to Saturn in about 1 year. Even then, as we approach the planet, a new invisible barrier would emerge before us: Saturn's radiation belts. These regions are filled with highly energetic particles capable of penetrating part of a spacecraft's shielding. They damage electronic systems and pose a major risk to living organisms. Earth also has radiation belts, and they already represent a significant danger to satellites and astronauts. However, Saturn's radiation belts are far more intense. Part of this radiation is absorbed by the planet's rings, but only a fraction of it. Still, let us imagine the unlikely. We build a spacecraft with perfect radiation protection and complete this long journey. What happens next? Before we even approach the planet itself, we encounter another invisible yet extremely dangerous obstacle: Saturn's magnetic field. It extends for approximately 1,000,000 kilometers toward the Sun and functions as a gigantic cosmic trap. The dimensions of Saturn's magnetosphere are incomparably larger than Earth's and would be capable of causing serious damage to electronic equipment lacking adequate protection. One of the most surprising characteristics of this magnetic field is its almost perfect symmetry. On Earth, the magnetic poles are clearly offset from the geographic poles. On Saturn, however, the magnetic axis aligns almost perfectly with the planet's rotational axis. Scientists believe this extraordinary symmetry is related to the presence of a special helium layer deep within the planet, acting as a kind of stabilizer. For a long time, this peculiarity made it difficult to determine Saturn's precise rotation period, since the magnetic field is usually one of the primary indicators used for such measurements. Only the data collected by the Cassini probe made it possible to solve this mystery. But understanding the magnetosphere does not make it any less dangerous. Saturn has a moon called Enceladus, which ejects gigantic jets of ice into space. These particles are captured by the planet's magnetic field and accelerated to astonishing speeds, creating an additional threat to any spacecraft attempting to approach. But let us imagine that we somehow overcome all these obstacles. Do you believe the landing would happen without problems? Let's find out. Our imaginary spacecraft, after conquering every challenge, finally enters Saturn's orbit. Before us appears, in all its grandeur, the majestic gas giant surrounded by its brilliant rings. And it is precisely at this moment that we encounter the greatest problem of all, the one that renders every effort made so far meaningless. It is impossible to land on Saturn in the conventional sense of the word. The planet simply does not possess a solid surface like Earth, Mars, or even the Moon. Saturn is a gas giant composed primarily of hydrogen and helium, along with small amounts of methane. Other elements, such as ammonia and water vapor, are present only in relatively minor quantities. Everything we see in images of the planet corresponds only to the outer layer of its extremely thick atmosphere, the tops of ammonia clouds. Beneath them, there is only more gas. This gaseous ocean gradually becomes denser until it acquires liquid-like characteristics. Attempting to land a spacecraft on Saturn would mean beginning an uncontrolled descent into what appears to be an endless abyss. To understand the fate of any equipment that attempts to dive into the planet's atmosphere, let us follow this imaginary fall. Let us begin with temperature. In the upper layers of the atmosphere, where pressure is still relatively low, extreme cold prevails. Temperatures range from -185 to -139 degrees Celsius. Any ordinary equipment would quickly freeze. But this is only the beginning. As we descend deeper, pressure and temperature rise rapidly. Saturn's atmosphere is extremely dynamic, with winds that can reach speeds of up to 1,800 kilometers per hour. For comparison, the most destructive hurricanes on Earth typically exceed only about 250 kilometers per hour. On Saturn, these supersonic winds are a routine part of the planet's atmospheric behavior, and would be capable of destroying virtually any probe before it reached the deeper layers. But what lies beneath? Let us suppose our extraordinary spacecraft can withstand this stage as well. It continues descending, and conditions become increasingly extreme. At approximately 1,000 kilometers below the visible cloud tops, the temperature already reaches around 730 degrees Celsius. That is enough to melt many of the metals we use. The pressure becomes so intense that hydrogen, normally found in a gaseous state, transitions into a liquid state. And this is only the first stage of the journey toward the center of the planet. At a depth of approximately 20,000 kilometers, the pressure exceeds 1 million atmospheres. To visualize this number, imagine that every square centimeter of the spacecraft's surface is supporting a force comparable to the weight of about 1,000 automobiles. Under such immense pressure and temperatures approaching 6,000 degrees Celsius, hydrogen assumes an entirely different form. It transforms into liquid metallic hydrogen, an exotic substance that exhibits properties similar to those of molten metals. This layer surrounds the planet's core and is precisely what generates Saturn's powerful magnetic field. The movement of charged particles within this gigantic metallic ocean produces colossal electrical currents, which in turn give rise to the enormous magnetosphere. For our imaginary spacecraft, all of this would mean only one thing: total destruction. Any material currently known would be crushed and melted long before reaching this region. At the center of the planet, according to scientists, there is a solid core composed primarily of iron and nickel. It is surrounded by a layer of heavy elements, and may possess a mass between 15 and 30 times greater than Earth's. The temperature of this core reaches nearly 12,000 degrees Celsius, approximately 2.5 times hotter than the surface of the Sun. In other words, Saturn is hotter on the inside than our star is on its surface. Any probe diving into the planet's atmosphere would first encounter an environment of extreme cold. Then, it would be struck by devastating winds. Next, it would be crushed by unimaginable pressures. And finally, it would melt under temperatures capable of destroying virtually any known material. But do you know what the weather is like on Saturn? That is exactly what we are about to discover. Beyond the obvious physical obstacles, Saturn fascinates scientists because of its enormous number of mysteries. One of the most intriguing and visually impressive is the famous Saturn hexagon, a gigantic hexagonal formation located at the planet's north pole. Discovered in 1980 by the Voyager probes, and later studied in detail by the Cassini mission, this structure is a stable atmospheric vortex with an almost perfectly hexagonal shape. At its center, a powerful polar hurricane spins endlessly. Wind speeds reach approximately 200 miles per hour and, in the central region, can climb to about 335 miles per hour. Saturn's winds are roughly twice as fast and up to 4 times more intense than those observed on Earth. But the most surprising aspect is something else. While hurricanes on Earth are constantly moving, driven by atmospheric currents and the planet's rotation, Saturn's hurricane remains fixed above the North Pole. Scientists still do not fully understand the mechanisms responsible for this extraordinary stability. Studies indicate that the roots of this vortex extend deep into the planet's interior, ensuring its persistence over enormous periods of time. It is a unique atmospheric formation in the entire solar system. Even so, there is a plausible explanation. The hexagon appears to be the result of complex atmospheric processes, a gigantic standing wave formed by differences in wind speeds at various latitudes of the planet. And what about Saturn's rings? They remain one of the planet's most fascinating and mysterious features. When discussing Saturn, it is impossible to ignore its most famous element, the ring system. It is the most recognizable planetary structure in the entire solar system. The rings are extremely thin formations composed of billions of particles of ice and space dust orbiting the planet along its equatorial plane. The main rings are identified by letters of the Latin alphabet in the order of their discovery, with the brightest and most visible being rings A, B, and C. Viewed from Earth, they appear to be continuous, solid structures. In reality, they consist of countless individual particles, ranging in size from tiny grains of dust to blocks of ice, comparable to multi-story buildings. Their composition is also of great scientific interest. More than 90% of the rings are made of water ice, containing small amounts of rock and organic compounds responsible for their characteristic coloration. The origin of the rings remains a subject of debate among researchers. One of the most widely accepted theories suggests that they formed after the destruction of an ancient moon that ventured too close to Saturn and was torn apart by the planet's gravitational forces. This hypothetical moon has even been given a provisional name, Chrysalis. Another hypothesis proposes that the rings are remnants of the primordial cloud that gave rise to Saturn itself. Whatever the correct explanation may be, they are estimated to be between 100 million and 200 million years old, making them surprisingly young in cosmic terms. But Saturn's rings are not just spectacular. They also represent an enormous danger to any spacecraft. Although most of their mass is concentrated within an extremely thin layer, passing through them without risking a collision with larger fragments is virtually impossible. The Cassini probe was the first, and to this day, the only artificial object to venture between the planet and its rings. Any attempt by a crewed spacecraft to repeat this feat would likely end catastrophically. Ice fragments traveling at tremendous speeds would turn the spacecraft's structure into a sieve within seconds. Furthermore, the rings are not permanent and unchanging structures. Under the gravitational influence of Saturn's moons, gaps appear within their composition, while part of their material is slowly drawn into the planet. According to some estimates, within approximately 100 million years, the rings may disappear completely. But Saturn is not known only for its rings. The planet also possesses an impressive collection of moons, and it is precisely on them that one of science's most fascinating questions emerges. Could life exist within this system? One of the most popular myths suggests that organisms resembling enormous floating balloons could inhabit the upper layers of Saturn's atmosphere. While this idea is fascinating, reality is quite different. The conditions within the gas giant's atmosphere are incompatible with any known form of life. For that reason, the hope of finding life in the Saturn system is not connected to the planet itself, but rather to its moons. Saturn has more than 80 known natural satellites, but two stand out above all the others. The first is Titan, a moon with a diameter nearly twice that of Earth's moon. It attracts attention because it possesses a dense atmosphere composed primarily of nitrogen mixed with methane. The pressure at its surface is about 1.5 times greater than Earth's, while the temperature remains close to minus 180 degrees Celsius. But Titan's most remarkable feature is the presence of seas, rivers, and lakes. The difference is that they are not made of liquid water. Instead, they consist of liquid hydrocarbons, primarily methane and ethane. Titan is the only known world, besides Earth, that possesses stable liquids on its surface. The second candidate for hosting life is Enceladus, a small icy moon approximately 310 miles in diameter. Despite its modest size, it provided one of the most extraordinary discoveries in the history of space exploration. From enormous fractures located near its south pole, gigantic jets of water vapor and ice particles mixed with organic compounds are launched into space. These geysers, known as cryovolcanoes, reveal the existence of a vast ocean of liquid salt water hidden beneath the frozen crust. Studies indicate that this ocean may contain all the fundamental ingredients for life: liquid water, organic compounds, and energy sources. This makes Enceladus one of the most promising places in the entire solar system in the search for extraterrestrial life. It was precisely because of this discovery that Cassini's fate was ultimately decided. Scientists feared that, after running out of fuel, the probe could lose control and accidentally collide with Enceladus or Titan, contaminating these worlds with Earth microorganisms that might still be present aboard. To eliminate that risk, the decision was made to direct the probe into Saturn's atmosphere, where it would be destroyed. But did the exploration of this mysterious planet end there? During the 13 years it remained within the Saturn system, Cassini completely revolutionized our understanding of the planet and its surroundings. It transmitted gigabytes of scientific data and hundreds of thousands of images back to Earth, allowing scientists to study its atmosphere, rings, and moons in extraordinary detail. Perhaps the most exciting phase of the entire mission took place during its final months. On April 22, 2017, Cassini began a series of 22 extremely risky flights between Saturn and the inner edge of its rings. No spacecraft had ever dared to enter that region. These passages, known as the Grand Finale, provided unique data about the composition of the upper layers of the atmosphere, the structure of the magnetic field, and the total mass of the rings. On September 15th of that same year, after executing its final command, Cassini plunged into Saturn's atmosphere at an astonishing speed. Friction with the atmospheric gases heated the probe to extreme temperatures. It became a brilliant meteor and vanished forever into the depths of the gas giant. The last signal transmitted by Cassini reached Earth 83 minutes after its destruction. The mission's success inspired new proposals for the exploration of Saturn and its moons. Today, several promising projects are under development. Among them is the Dragonfly mission, which aims to send a rotorcraft to Titan capable of flying across the moon's surface while investigating its atmosphere, terrain, and chemical composition. Future missions to Enceladus are also being studied, with the goal of collecting and analyzing samples of the material expelled by its cryovolcanoes. However, all of these projects are still in the development phase. It will take many years before they become reality. But do you know what is even more impressive? After unraveling so many mysteries, we arrive at the most surprising conclusion of all. Even if it were possible to reach Saturn and land on it, there would be no way to return. And do you know why? Saturn is a gigantic planet. Its mass is approximately 95 times greater than Earth's. Although gravity in the region of the visible cloud tops is only slightly stronger than Earth's, the real problem lies in what is known as escape velocity. This is the minimum speed required for a spacecraft to permanently overcome a planet's gravitational pull. On Earth, the escape velocity is approximately 6.9 miles per second. That is why we need gigantic multi-stage rockets to place satellites into orbit and send them into deep space. On Saturn, this speed reaches about 22 miles per second. That is more than 3 times higher than Earth's value. Achieving such a speed would require a rocket of extraordinary power. But the main problem is not even that. To launch, a rocket needs a solid surface to push against, and Saturn does not have one. Any spacecraft that descends deep into the planet's atmosphere would be doomed to remain there forever. And so, we conclude our journey through one of the most extraordinary and terrifying worlds in the solar system. We have discovered that Saturn's beauty is as fascinating as it is deceptive, and we now understand why it can be considered a true cosmic trap from which there is no escape. But that does not mean we should stop dreaming about it or studying it. Quite the opposite. The more we learn about worlds like Saturn, the more we realize how rare, precious, and fragile Earth truly is. Exploration of this giant continues through telescopes, observatories, and future space missions. And who knows how many secrets are still waiting to be revealed. Subscribe to our channel so you do not miss new fascinating investigations, and continue exploring with us the most incredible mysteries of the universe. Many extraordinary discoveries still await us, and without a doubt, we will embark together on new journeys to uncover them. Until next time,